Hi everyone, this is Kurt with Hypnodyne. Today I would like to introduce to you the first joint recording, synchronized recording between ZMax, our forehead-worn EEG system, and Airmax, which is a respiration-focused wearable. There's a lot going on here, so I'm going to try to keep it simple, but it's not necessarily something I'm really good at. I want to first of all get this out of the way. If you record EEG on the forehead, oftentimes you're going to have problems with sweat artifacts. What you see right now here, you have two EEG lines. I mean, every track has two channels, left and right. The one at the top is what the device acquired, and the one at the bottom went through our AI model for removal of sweat artifacts. These are the sweat artifacts here, 1, 2, 3, 4, 5. It works really well because the things that are not sweat artifacts like this one were left completely intact. Stuff like, rapid eye movements, they're completely intact. Only sweat artifacts are removed. So it's a really good system. So for now, I'm just gonna remove the I'm gonna remove the one that has the artifacts, and I'm gonna just leave the other one. So main problem is we have different systems and paradigms for viewing these two devices on the software, which is called HD Scorer. So for now, and this is very temporary and tentative, what I do is just open both recordings, and then with the tracks open that I want to transfer over, I push T, but don't quote me on that. The hotkey might change, but we need to make some room here to have those ZMax tracks. Also, I'm gonna go to X-ray mode because this is a person with weak spindles, so it helps to have the X-ray mode on. And as we do this, the first thing that I would like to do, in fact, let's remove a bunch of things, and we're just gonna go through the accelerometer data. In my previous video, I explained how you can double check that synchronization works. And that had to do with plotting the derivative of the two accelerometer signals side by side and verifying that any spikes corresponding to position changes would be coincidental. When you already have the aligned signal, you can look at that more in detail. You can just scroll so that you can see that when there's disturbance on one accelerometer, you also see on the other one. The reason this is blocky is because Airmax is a lower frequency rate or lower sampling rate. But as long as they coincide at the beginning of the recording and at the end of the recording, you're doing good and everything is aligned properly. But when you're scrolling like this, you can do something else. When you push the down key, you're able to toggle the filtering. If you toggle the filtering, the accelerometer has a lot of range. So you have to use the scroll wheel to zoom out to what you want to see. But the good part is that, you see, the big movement is about in this region, this area. But even before, the person is already starting to rotate, well, their head probably. And so if you scroll in this modality, you're able to view body position changes with a lot more detail and really see that the deflection of these accelerometric signals do in fact begin at the same time without necessarily relying only on this kind of spindle type blob that happens with filtering. And you can move through and you will often find very distinctive shapes that the accelerometer lines are making. Like this one, or like this one. So this is very good to do, to be able to see that in fact the alignment is perfect. The reason you want to make sure of that beforehand is that once we close these, if anything is misaligned, we're not going to know. So you check that first. And now we reintroduce all the other stuff. So let's start by bringing in the EEG and the respiration. don't know why I can't close that anymore. We do it again. So we have the EEG here, then I want the respiration. Now, as you know from my other videos, with Airmax, when you save the file, which is when you finish the recording, it outputs some markers. Think about them as bookmarks. And we're going to open two bookmarks. The process of synchronization also modifies those markers, because obviously you want those to get synchronized too. But this is the synchronized version. We have two marker tracks. In white are the detected apneas. And so, for example, it's telling you that it found an apnea right here. This is a flatline condition on the signal. In green, we have the stimulation. Now, I'm going to tell you about a little glitch that happened, a very fortunate little glitch. What I said in one of the previous videos is that probably you shouldn't use device stimulation values under 3, because it's a small vibrating motor, and if you just give it a very small current, it can kind of jam for a while. Turns out 3 is kind of borderline. You probably don't want to do 3 either. Because what happened in this recording is that we had a stimulation at level 3, this one right here. See, DV3, this means device vibration 3. Device, because it's vibrating the Airmax. As you know, you can also choose to vibrate your mobile, though I'm not sure why you would want to do it that way. You can also play a sound on the mobile. That's something you can do too. With device vibration is nice because you're going to have proof that it happened right here. But anyway, this last DV3, it jammed the little motor. And so here there's a long apnea. It thinks it's stimulating. All the markers are there, but you can see nothing on the accelerometer. And that continues until we get here. So from here, roughly, to here, this becomes a sham stimulation period. That is, everything else works exactly the same, but the motor is not functional. The reason that was a happy accident is because you can see the difference between the number of flatline events that occur in this no stimulation zone versus the rest of the night. This particular person, we've done at least 4 or 5 nights with him. This is the first night where we managed to synchronize the EEG, which is what I wanted to show you eventually. We're going to talk about the EEG in relation to sleeping, in relation to breathing very soon. But for now, the thing that really pops out is that when the stimulation became sham, look at how many apneas and flatlines. So, hey, first of all, this is not medical advice, so don't trust anything I tell you. I'm just looking at signals is all I'm doing. But, you know, these thermistors that detect the airflow at your nostrils, they're a very simple component. I mean, that has no chance of failure, like not showing it if you're breathing. If you see it flat, you're not breathing here. And second of all, I'm going to be speculating because a lot of this stuff, like, I don't know who's doing this kind of experiment. So I'm just telling you what I see. It seems to me, and maybe you can see it better if I zoom out a little bit more, but you can get trapped in this state where you have one breathing interruption after another. You start, you stop, you start, you stop. And you're in this roller coaster from, I can tell you how long it lasted. We can tell you exactly. So from midnight to, 45 minutes. From exactly midnight for 45 minutes, this person got caught in a really bad spiral or loop or however you want to call it, but the apneas keep coming and coming and coming. Without the stimulation. With the stimulation, hey, little flatline condition happened right here. Okay, breathing for a few minutes. Now there's stimulation here, a little movement. And then he was back in business and no interruptions for a long time. Then it happens again. and see here, and look for how long normal breathing is restored. Am I saying buy Airmax today because it's going to fix your breathing? No. But other than getting a CPAP, I really don't know what you could try. These are results on only one person, by the way. So I want to stress this. I'm not telling you anything about what this is going to do or not going to do. I'm just telling you what the data is showing me right now. The data is uncontroversial. The sham stimulation period is jam-packed with flat lines, and all the rest is very sporadic. And they're small too. And honestly, sometimes the trigger is just because, this area, okay, there's 5 seconds there when it was pretty much flat, but still looks like sort of nice breathing. Another thing that I found is very interesting is this. Let me open the, we want to open BPM. Usually if you click a track and then you click it again, it shows and hides it. But if you hold down Control and you click it again, you get 2. You say, why do I need 2? Because then you double click one of them and that's showing you in this epoch the same signal. One is the whole night overview and the other one is this epoch. So I can scroll and you can see both. Okay. So I thought that by applying this little stimulation, there would be a sudden, if not an awakening, at least an increase in heart rate. And to be sure, maybe slightly that is the case. So 54, 60, like 50, let's say 55 to, well, actually 67 is, let me open the PPG so we know that we're looking at something that makes sense. I'm going to need to zoom in a little bit. So let's say that our baseline before the flat line was 57. After this little stimulation is 65, 66, maybe 67. So you have a slight increase in heart rate, but if you look at the PPG, it's almost invisible. But I think we can trust the calculation. So let's say that it's 57 to 67, so it's plus 10. Now let's go to see what happens when you do not interrupt a flat line. Need to find one where it's clearly visible, and now it's getting messy. Maybe I have to zoom out. So here we go from 60.5 BPM, right, 63 here, 6, to 73. So it seems like not breathing for this long a time during the sham period where there's no stimulation causes an increase in heart rate that's a lot more dramatic than just the stimulus, just the vibration. Let's pick another one to see if that's still the case. Here we have again plus 14 BPM. Try this one, 16. So here we have a heart rate increase of 16 BPM after the breathing resumes without stimulation. So it really seems like the question, does the stimulation bother your sleep? It seems like it bothers you more to not stimulate. Because here we have 10, 11 versus up to 16. Let's pick another one. In this case, there was an increase of 6 BPM before and after the stimulation. Now, is that terribly surprising? No, maybe, because if you really stop breathing for this long a time, yeah, your body, before you actually start breathing again, your body, I think, is in a state of slight shock, for lack of a better word. So yeah, it doesn't surprise me too much now that I'm looking at it that the apneas without stimulation actually cause an increase in heart rate that is superior to the stimulation. All right, let's close some of this stuff and take a look at the EEG. And for the EEG, we need the normal 30-second epochs because that's how everybody's used to looking at EEG. So here's the cool thing about the synchronization, that now you can see the EEG spectrogram and the EEG track and the stimulation markers, and now you can say what happened before and after the stimulation. Now in this case, remember, we're in the sham area from here to here, so there's actually no stimulation here. There's simply an apnea that just ended by itself. And look at this. So this is clearly not a stimulation. This is body movement. Why is the body moving? Because there was this event, 30 seconds without 21 seconds without breathing. Actually, this is the live mode, so you have to add 5. Like, this is the length of the detection. So add 5 to that. So that's 26.6 seconds apnea. And after that, you start breathing again, but the person is moving slightly. That's interesting because it shows you that there's some kind of arousal. I could interpret these as slow eye movements, which would corroborate an arousal. To be sure, I look at before the body movement and see what we see. And I would say that we don't have the same kind of pattern. So I would say that this is an arousal, both in terms of slight movements. See, the lines are not crossing, which means the body position is the same. There's just a slight movement. And that's what happens after a sham that is no stimulation. Again, here we have slight movement. If we go and take a look at actual stimulation apneas, what happens after the stimulation? Well, nothing. There is no movement. Isn't that interesting? So that means that the stimulation has caused less of an arousal than the actual spontaneous end of the apnea. However, in this case, the apnea was 5.96 seconds, and the one we were looking at before was 26 seconds. Now, if you have a keen eye, or even if you don't really, you can see the heart rhythm superimposed on the EEG. This is just a recording artifact. It doesn't really matter for our purposes. Maybe the headband was a little bit too tight or not tight enough. But that's the heart rhythm superimposed on the EEG. We can take a look at more episodes. So here we have a real stimulation. And the brain activity before and after looks very, very similar. I'm not seeing any change. Here's a major body movement with EEG disruption. So that's anomalous. We don't look at that because it's actually the person moving. Here's another stimulation followed by, gosh, I wonder what these are. They look like eye movements, but it could be REM sleep because they're not that sharp. And in fact, we are at the end of the night in a, I would say, sort of mixed period where you have spindle activity, but relatively few, relatively sparse. Obviously, I'm not showing you what I planned to show you just because I can't possibly remember on a recording where all the stimulations are. But I've taken a look and now I'm going through it again one by one, seeing what I can find. So in this case, arguably, maybe the 5-second window is not long enough for detection because I think he was probably going to start breathing again after this. But there was a stimulation and the brain activity after that, same as before. So this is an example again of a stimulation that caused absolutely no body movement and absolutely no change in EEG. So what I gather from this, look, obviously it depends on the person. There might be a person for whom this kind of vibration on the nose, it wakes you up. But at least for this person, not only do we have plenty of stimulations that are followed by no change in EEG and not even like a jerking of the facial muscles, no movement at all. And at the same time, the apnea is over. But also, you see that if you go look for arousals, the sham period, the no stimulation apnea, that is after 26 seconds of not breathing, that causes much bigger arousal or a much higher chance of a body movement than the stimulation. These are more shams towards the end. This is a 16-second self-terminating apnea with sham stimulation, because here again we have a motor jam. And it always happens after a strength of 3 stimulation. So I would recommend using a strength of at least 4. And the idea behind trying to start as low as possible is I had no idea how much it would disturb sleep. So my idea was start from something that's nearly imperceptible. But unfortunately, a motor that's small enough to fit on the Airmax is not mechanically extremely reliable. So you gotta give it a little bit of current, like a minimum amount of current for it to not get stuck. Another interesting thing, this white line is the head position. And if you look at the apneas, he's facing to his side. So he asked me, do I have more apneas when I'm facing up? And I told him no, because this big chunk all happen when you're facing to one side. And these clear areas, same kind of position. Maybe there's something wrong there with the calculation. Oh, no. That's because he's face down right now. That's what's happening. He's face down? He is. Interesting. I think the way this line is calculated needs some tweaking. But anyway, these are the various sleeping positions. So if this was your recording, what would you understand? You would understand that you have a pretty regular sleep EEG. There's nothing really to say much about the EEG. You would know that you're not producing alpha waves from the front of the head, because during wake there's no alpha. You would know that your SpO2 is dropping a lot. And that during these periods, particularly without the stimulation, it's going down very frequently. See these big chasms? That's a drop of 6 points. There's a drop of 4 points. There's a big one. There's a drop of 9 points. Now you might say there's only one value that actually is that low. So you might say, is that even a legitimate value? So what you do, if you're in doubt, you come here and you look at the PPG and you ask, is that PPG actually working? And it is, because do you see how here the two colors are exactly the same amplitude? And here, when you're in a good saturation region, the yellow or light orange is a tad larger than the dark orange. This one peak, the dark orange is actually bigger. I would take the average between these two as a value. I would say that this is 95.78. There is a limit to the resolution of the SPO2 computation because it's based on peaks. You can only calculate a value every time there's one of these peaks. So one thing you can do is smooth it. Honestly, any pulse oximeter you buy is going to be smooth. And I don't do that because I like to go in and see the detail, but if you want to smooth it, you can. So if you do it like this, it's a little bit more well-behaved, but you might miss some detail. So let's say that it's like this, actually. But this is a way in between. The good part is you don't have to look at two values. You just select, and it tells you the delta. Anyway, back to the overview. We're almost done. So if you got this in the morning after wearing ZMax and Airmax together, you would know that you have a bunch of apneas. You would know that you had some stimulations for some reason. And what I would suggest if you had this, what we're going to do with this person is try it again and again and again to see exactly, is this something that repeats every night? Because it's almost too good to be true that when the stimulations are applied, there's almost no apneas. So I don't even want to believe it until we get the same result many, many times. But that's what the data is showing, is that they're all focused in this region of sham stimulation. Then you would also see that you could say this period here to here, if you look at the EEG, is a little bit anomalous because it starts at 10 p.m. and it ends at 2:30 a.m. So that's 4.5 hours without any big chunks of REM sleep. I mean, you could say these are small chunks of REM sleep, but it's kind of weird. Like, this is a normal sized chunk of REM sleep if it was from here to here. And also from here to here, even though here it's going back and forth, you see these spindles here in the middle. But here to here, that's kind of long. But I'm not saying it's concerning, I just noticed it because it's very long. What else? We established that there hardly seems to be any difference in the EEG before and after a stimulation. And actually, I used another software to do a spectrogram with a much narrower window size. I used 512 to really zoom in on the spectral component and see if there was even the tiniest discernible difference between the before and after the stimulation, or if there's any high frequency activity indicating an arousal. But at least on this person, okay, I'm not making general statements, but on this person I really did not see anything. Maybe what you could interpret that as meaning is that if we didn't have the respiration, if you look at this EEG, you wouldn't know what's going on. You wouldn't know that you're getting stimulated, and you wouldn't know that you're having breathing interruptions. So this is all very interesting. I'm going to go over one last trivia or interesting aspect. As you know, ZMax also has a PPG. This is on the forehead. Now, what would happen if we plot side by side the PPG of Airmax and the PPG of ZMax? And here's a bit tricky, so I'm just going to be very speculative for this because it's the first very good alignment that we got. So I hope that there's not still a latent misalignment, but everything that I'm seeing points to the idea that these two recordings now are perfectly aligned to within milliseconds. Now, if that's the case, I noticed something very interesting, which is that at the beginning of the recording, the bottom of the PPG on the forehead is almost perfectly aligned with the bottom of the PPG signal on the nose. If we go even earlier, again, they're almost perfectly aligned. But there are places, such as, if I remember correctly, it was around 7,000, where there's kind of a big gap. Okay. And by big, I mean not huge, but there's 0.2 seconds gap between one and the other. And it's changing all the time. And I plotted the difference and I get out a curve that first of all looks biological. It's not a straight line, because a straight line would just mean that the alignment is not good. Also, I see that there's a sharp incline, or like a sharp increase in that delay at the sleep onset right here. And I notice that when the person wakes, which is right here, it drops off again. So there's some chance, but take this as the most speculative thing I'm going to say in this video, but there's some chance that plotting the phase difference between these two gives you an indication of either blood pressure or perhaps the activation of the sympathetic versus parasympathetic nervous system. And it could also just be that it's the sleeping position. Maybe one sleeping position gives you a better, I don't know, flow of blood, like but forehead to nose just doesn't make that much sense. Anyway, that's something that came out of the data. I fully expected this data to be redundant now, but it seems like if you plot the tiny differences in phase, like for example, the bottom here is over here, and the bottom here is over there. So now there's a difference of, it's plus 2.6 milliseconds. So it could mean something, and maybe it means nothing, but when I plot it, it looks vaguely biological. Honestly, to know for sure, we have to remove these interferences. When you see something like this, this is the breathing rhythm that's affecting the PPG reading, and it's distorting it. And that happens when the device is kind of coming off or not tight enough. As a comparison, this is very good signal. This is perfect because it's even bigger. And here it's good because it's big, but it's also fluctuating with breathing. So if I had a recording where it's all like this, without any breathing interference, then I would be maybe a bit more confident that we're looking at a biological type of signal. But for now, it's just speculative. Anyway, pretty normal sleep. Very, very long first cycle for some reason. And the most salient thing is this. We got sham stimulation. So same person, same night, same device. And the part with no stimulations has a lot more difference in the heart rate, which probably we should open. This is the heart rate. So the idea that you continue to have speed ups and slowdowns, it's shown by how it's coming up and down, probably here too. And this PPG looks very good. So that's... And we can do another trick, because this is the same recording, but it's just a ZMax signal. We go to HR, which is the heart rate. And now we have the heart rate computed from the ZMax signal and the heart rate signal computed from the Airmax signal. And they are identical, which only happens if they're both good. If one of them is bad or two of them are bad, they would not be the same. So there's a lot of variability here. There's also, honestly, a lot of variability here too. And here we don't have breathing interruptions, and we also don't have stimulation. And it's also not REM sleep, because it could have been REM sleep. If you didn't have the EEG, I would have said this is REM sleep, because it's got so much variability in the heart rate. But REM sleep starts here to here. And so why is there so much variability? How can it be? We don't really know. The EEG looks fine. It looks like restful sleep. I don't see any arousals. And we definitely don't have apneas in this region. You know what? Maybe I misspoke. Maybe we do have them. See, Airmax allows you to detect apneas when the respiratory signal flatlines. But what do you say in these cases? Because in these cases, there's definitely breathing here for sure. It is stuck in the same pattern we were looking at before, but much less so. So instead of breathing and then flatline and breathing and flatline, it's just decreasing and then it increases again. So what do you do then? You open the SpO2 to see what is going on. And these are actually affecting the, let me filter it. It's 8.5, no. It's a bit too much, 0.2, okay. So look, there is a difference between breathing a lot and breathing a little. How much difference? 2 points of SpO2. So Airmax did not detect these. Of course you can find them in the recording. You can also change the threshold, but the problem with changing the threshold is that then if you go to areas like these, then it would say it's always apnea. So you really want to set the threshold so that you're detecting the flat lines. And honestly, if you get 2 points of desaturation, probably not such a big deal. But what this is telling you anyway is that once this happens and you come out of it and you start breathing again, your heart rate goes up. Isn't that interesting? Because that kind of points to what is creating this. Like what happens when an apnea terminates? There's evidently some nervous system activation that is able to bring that about. So you go from 48 BPM to 68 BPM. That's a huge jump. The heart rate here is going up by 20 BPM every time the breathing is restored. But here's, again, it's fascinating that during the sham, it would just continue to happen. Then, after the stimulation resumes, it's like it's kind of shy, it doesn't want to do it anymore. Maybe it's afraid of getting the stimulation. I don't know. I'm just joking here, but you know, this is stuff that you would need a large study, and you would need somebody to look into this in detail. And I don't think anybody's doing it. I mean, if you're a researcher and you want to do it, I've got devices to sell. But for people that are not doing this type of research, you know, we're not going to have the answer anytime soon. But what you can do is to just get your own device and then observe what happens with the stimulation, what happens without the stimulation. And then you can change some lifestyle parameters. If you drink alcohol, what happens if you don't drink alcohol? Or if you do swimming versus weightlifting, how does changing anything, how is that able to influence these? As an example, if you were able to go from this with all the flat lines and drops of like, well, here it's a 4%, here it's kind of 4%. We're in the 4% ballpark here, I guess. But you know what, this is why I do it on a peak by peak basis, because when you smooth it out, the part that gets most smoothed out is the bottom, because oftentimes you only have a couple of peaks at the lowest SpO2 level before you start breathing again. That's why I like to do it like this, which is actually much harder to compute, because you have to really split the peaks very carefully to be able to do this. But if you do it like this, then you can really catch the bottom. And if you catch the bottom, okay, it's still 4.62. So these are actually not very severe. Do we even have very severe ones? This is 5.3 drop. This is only 4. So actually these are not severe apneas, but they're still flat lines. This one maybe. This one has to be huge. No? I think I just zoom in too much. That's what it is. Anyway. Like if you're able to move from something like this through, whatever life hack. If you're able to move from something like this to, where was it again? I think it was here. Yeah, something like this. You know, because here, yeah, is it trying to stop breathing? Is your body is trying to stop breathing, but it's not going all the way. So you still get a heart rate spike at the end of that, but it's happening before you can actually totally desaturate. And if we look at the delta here, I think before it was around 4 to 5. Here it's 3, so it doesn't make that big of a difference. I know for a fact the subject has much worse apneas because we had them in the other nights, but this is the one night that we're looking at because it's got the EEG synchronized. But he's seen worse actually. All right, I think that was enough. This is a whole world of biosignals. A lot of this stuff, you know, I have to tell you, I'm not a doctor, so I don't know what I'm talking about. So don't believe anything you hear on here. But on the other hand, okay, where's the doctor that's gonna have seen this type of stuff, especially with the stimulation? Well, we don't have any. So, you know, you could use Airmax to collect the data and then show it to a doctor. But I wonder who's even gonna have the time to look at data with this level of detail. Anyway, I gave you, you know, I'm just a humble hardware manufacturer, so I have the device. I'm showing you the data so that you know what the device does and doesn't do. We seem to have a few little problems with the motor jamming. We're going to try to resolve them by eliminating this DV3. Stick with DV4. And even so, it's good because if you have a sham, you can really compare with the rest of the night. And in this case, it was very useful. No stimulation, bang, bang, bang. One apnea after another. Rest of the night, very sparse. And I think all this is quite interesting. We've established that the stimulation is not too disruptive of sleep on this person, this particular subject. But also in many cases, not stimulating causes a much bigger heart rate spike than stimulating. So that was unexpected. Okay, that's all I have for you today. Hope it wasn't too long. Thanks for watching.